All right, hello everybody. So today the focus is going to shift from concurrency control theory and sort of looking at transaction in the context of centralized system, basically moving on to transaction distributed setting, and have a look at the emerging field of blockchain. So we're going to spend about a lecture or two on this topic. And then we will move to the final topic of the course, which is going to be on the query language. So let's get started. Just kind of a little bit in terms of research that is happening at UC Davis, because blockchain, I think, would be probably one of the most important area in databases, and it could be one of the important area in computer science in general. And the focus at UC Davis in database group or the exploratory system lab that I run is really to look at and develop and pioneer a resilient data platform and be able to do this at scale. And you've already seen a flavor of this research, which is LStore, is to be able to do transactional and real-time analytics. And so that was the work that was done early on. And now sort of the next stage of this work is ResilientDB. And here is really focused on a really fundamental problem of what if you could do computation in a democratic and a decentralized way? Democratic in a sense that you don't have the power of making the final determination by a single entity, like a single bank, and decentralized in a sense that not all the data, not only that a single bank won't make all the decision, but also that single bank won't be the only place that the data gets stored. And you can look at this as essentially a paradigm shift in the way we do transaction, or a paradigm shift in the way we do computation in general. So you can really, I think, expand this to much broader scope. And so that's the focus of the lab. And we do a lot of exciting research when we partner with different blockchain company to explore and look at the transfer of the technology and see its impact in industry as well too. And always looking for a creative and sort of excited student to pursue this research. And even the last time we offered 165, actually since then, 2 undergraduates have joined the lab and they are working on this topic as well. Of course, master students, new master students come every year as well to join the lab every year. But from 165 last year, we have 2 students that have really done really interesting work on the problem of the consensus, which is at the core of blockchain. And they've also been looking into the relationship between consensus, blockchain, and serverless computing. In a sense, how would you bring fault tolerance into serverless, such as function as a service or Lambda or microservice architecture? And that's, I think, serverless itself is a very, I think, exciting paradigm shift in the way we think and develop software. We build scalable software, and now kind of the connection between these two emerging fields. Any questions? In general, just kind of, at least for the folks who are on the call right now, how many people are familiar with blockchain, or how many people have heard about it? Just kind of hear a little bit of a background in terms of your, yeah, just in terms of background, if you could share, that would be great.
Got a little bit of knowledge, but just kind of as it relates to decentralized finance platforms, right? So like ledger distribution, I guess, and just kind of having transparency there. That's kind of it really for me. And that's just because of interest in like cryptocurrency, right?
Yeah, exactly. So the cryptocurrency, the DeFi, the decentralized finance, I mean, those are all exactly, that's what makes this field exciting. In fact, also last quarter, we run a course 189, and it was a really a collaboration between industry, and we had industry speaker from pretty much every blockchain company, every leading blockchain company coming every week, twice a week, and talking about their experience in developing and building blockchain platforms. You had over 25 speakers, and all the recordings are, of course, available online, and you can have a look. But it was a very exciting to bring everybody to Davis and have that conversation around uh, the kind of work that they are leading across the globe, not just United States. We had speakers from all the way from Australia, China, Europe, and of course United States and Canada. So lots of actions happening, lots of interesting things happening, but sort of the core, sort of the question is having this the need for the resilient platform. You could ask why we need it, and the relationship between the resilient platform and blockchain, and of course, what is it that we already have? And this is not a new topic. Folks in distributed system have been studying similar kind of problem for the last 30, 40 years. And but of course, with the crypto and the Bitcoin, there was a new thread of thought of how to reach or how do you build these scalable system. And of course, the question that we've been uh, focusing on is how do we improve it, and what new tools do we need to create to really make this technology available for prime time. And so one of the challenges, again, for those of you who may be familiar with Bitcoin and crypto, is that sort of the transaction rate that Bitcoin supports is about 7 transactions per second. Ethereum, another platform, another permissionless blockchain platform, or a public blockchain platform, again, we're talking about dozens of transactions per second. Even in your assignment, you may have noticed that you could get potentially hundreds, if not thousands, of transactions. In the state of the art transactional system, such as LStore or transactional concurrency control like Quick, we can get 5 million, 6 million transaction per second, or potentially getting 50, 60 million operation per second. So there's a huge gap getting millions of transactions per second versus just a handful of transactions per second. So there is that disparity that is really where the challenge and I think a lot of exciting work lies. Yeah, I guess some of you have kind of looked around when you were during the initial pre-milestone phase about blockchain, which I think is really good. And I think it's important to know it because uh, as you move on to industry, you may be asked that question when there's an interview, or whether in the job is that whether blockchain would be useful for uh, any particular task on hand. So I think this is a question that will be emerging and will be coming up, I think, sooner or later. So why do we need these resilient, high performance platform? Well, let's kind of look at the scope. Let's kind of look at in terms of sort of where we sit in terms of the different kind of the array of different type of protocol that we have. So in fact, what we're showing here, it's this chart that I'm going to explain. It doesn't talk about what we have studied so far. What we have studied so far, we looked at the problem of concurrency, we looked at the problem of transaction in a single machine. And we studied that the serializable theory and how do you do concurrent execution of transaction, and how do you talk about the correctness of that using the notion of serializability. We said we can execute transaction concurrently as long as we can show that this produced scheduled correspond to a serial execution. So that was the basics of what we have focused on. in terms of the transactional theory. When we're talking about the quick, we briefly touched upon what if the entire data cannot fit in a single machine, that you need to distribute it. And then we also briefly mentioned what would happen if you also need to have multiple copy of the data. So now, given that serializability notion, and going to maintain the same guarantee in terms of correctness, you want to still have an atomic transaction. We still want to have isolation, consistency, durability, all of those properties that we've talked about, they are still applicable here. But just the problem is becoming a little bit more uh, interesting, in a sense that we're now going to say that the data cannot fit in a single machine. So we need to have partition the data across machines. And we may also say that, well, even if I do the partitioning across machine, that's great. But what happens if one of those machines fails? How am I going to continue operation if there are failures? And then we're going to say, well, if there are failures, is it possible that there are some malicious failure, not just benign type of failure? And so that's where we kind of get started with 2PC. So that's two-phase commit. This is basically becomes an agreement protocol that allows deals with recoveries and crashes. And it also talks about the agreements in a sense that if the data does not fit within the single machine and I spread it across two different machines, so now I need to ensure there is an agreement that that fragment of the transaction that was executed in the first transaction was successful, and also the fragment of the transaction that was executed in the second machine was also successful. And in order to ensure the atomicity of the transaction, I need to ensure that both fragments were successful. So if I receive success on both, then I can decide that the fate of the transaction should be a commit. So that's the basic idea of the 2PC. And the other basic aspect of the 2PC is that, relating back to what we studied so far, is that if I have a consistent ordering of transaction, conflicting transaction on the first machine, that consistent ordering of that ordering that I have, that serializable ordering that I have in the first machine, must be consistent with the second machine. In other words, it says if I decide that the transaction T1 precedes T2, it also must follow the same order that T1 precedes T2 in the second machine, and then the third machine, and the fourth machine, and the fifth machine. So not only it's no longer that is enough that I have a serializable schedule, I need to make sure that that serializable schedule is also consistent across machine. And if one of the machine goes down, then potentially progress cannot be made. But once the machine goes up, then there needs to be a recovery mechanism that allows the machine to recover and the whole system to recover. So these type of protocol, whether it's a two-phase commit or a three-phase commit, they fall in this category, is that they assume that the data is spread across a set of machines, and they all ensure that there is an agreement that either all or none of the fragment of the transaction succeeded, and also there should be that they all have a consistent serializable order among the machines. These protocols specifically at that level of the agreement, they may not be concerned about that consistency of the ordering, but at least they need to ensure they deal with the fact that whether the fragment was successful or not. The consistency of the ordering is an additional problem that needs to be addressed as well. So that's the first step, is that I distribute my transaction across a set of machine, and there are protocols, these agreement protocol that allows all or nothing execution across machine. So now with this type of protocol, it allows me to, if I cannot fit my data in a single machine, then it allows me to spread it. It also may be that there are some regulation. For example, Europe says that European data has to be stored in Europe, and US says the US data has to be in US. So there may be also other reasons that you won't, even if you physically were able to put all the data in a single machine, because of the regulations, you may not be able to do that. So then again, there is a need of having a protocol or agreement protocol that allows us to execute these distributed transactions. So that's the first kind of dealing with crash recovery. Then there is a whole new flavor of protocol, which is under, they call Paxos. So the original one was Paxos, and they're all variation of this Paxos protocol. And the idea here is that, well, it's great with 2PC and 3PC. I can do distributed transaction and I can handle crash recovery, meaning that I can recover from crashes once the system is live again, or the machines are back on. But when things goes down, there's nothing really I can do, is because, well, the system is down. But what if we add replication? And what the replication is, well, I spread my data across two machines, but I have multiple copy of each of the machines. So maybe I have maintained 4 copies of each data. So that means in total, I would have 8 machines, 4 machines used for first half of the copy, the other 4 will be for the second half of the data. And there will be 4 identical copy of each half. So now I have a 4-way replication. And so not only I need to ensure that the data is consistent in the primary copy of the data, you may say. So I have one primary copy and then I have a bunch of backup copy. So not only I have to make sure that a transaction fragment is succeeded in my primary copy, and not only I have to make sure that I have a consistent serializable ordering on both copies, but I also need to make sure that my primary and my backup copy are also consistent. Because, for example, if your backup copy, for example, goes down, and if you want to use some of your backup, then the backup should be up to date. Otherwise, you will be missing certain recent transaction, and it will create inconsistencies. So these array of protocol, they look at resiliency in terms of crash resilience, meaning that up to F number of, they would say up to F number of replicas or the backup can go down, and the protocol will still continue to progress. So in other words, as long as the majority of the data is up, or the majority of the machines are up, then the protocol can make progress. The final category, which is kind of calling it here consensus, which is again is a form of an agreement, is to not just be crash resilient, but also be Byzantine resilience. And what the definition of Byzantine is that the type of the fault model that we look at is not just limited to crashes, it also malicious. Is that what if one of the replica doesn't send a message, or sends a wrong message, or delays the message, or reorders the message? Or what if the network does all of that? The network reordered the message, dropped the message, or any kind of malicious behavior, any arbitrary type of behavior can be expected, or any type of arbitrary behavior needs to be able to be tolerated. And of course, sometimes these malicious, it may not be that it was intended. There is a software bug that causes an arbitrary behavior that may look like malicious. Still, you need to be able to have fault tolerance that can deal with those type of failure. And so that becomes the final category. And the blockchain is sort of lies in this category of consensus. And so the problem of the consensus is, meaning now it comes back to this problem of reaching agreement in a democratic and a decentralized way, where You assume the majority of the society or the majority of the participants in this consensus are honest, and only the minority are malicious. And this is the assumption of the system. Of course, if this assumption or this premise is not met, the system will not produce correct results. We will lose correctness. But as long as this assumption holds that only the minority are could be faulty, then these systems can be proven to be correct. Any question? Again, just stop me any place that you can. This lecture is really going to be. We're not going to go to look at every details of protocols, but it's just going to give you an insight, an overview of this field. So please, anytime there's anything that you're unsure about, please ask.
Professor, so when you're saying that this, Professor?
Yes, I'm listening.
Oh,
yes,
yeah,
I can hear you.
So yeah, so when you say that there is consensus, does that mean that there are several machines or several entities that verify the validity of the blockchain on this distributed system?
Exactly, precisely.
Okay. And is that, this may be a little off topic, but is this also related to how the blockchain is maintained, like in relation to cryptocurrencies, and how like there is a Bitcoin mining and all of that?
Exactly.
Okay.
Let me give you,
you.
so those are really good questions. So maybe it's a good time to kind of give an analogy. So in a traditional banking system or a traditional way of dealing contract, you will have a bank, and that bank maintains a ledger. So any transaction that happens between, let's say, Alice give money to Bob, or Bob gives money to Alice, every transaction that happens, that bank, let it be Chase, Citibank, they will maintain a ledger. Sure, the ledger is a computer, but you can think of a ledger as just a notebook. So the bank has a notebook. It writes down its notebook that Alice gave $5 to Bob. And so now, and then this ledger may get multiple transaction, and it tries to write multiple transaction at the same time to this log. And when you're writing these transactions to the log, you may kind of start writing the first operation. Maybe Alex paid Alice $5, and then Alice is planning to ship a book, and then finally the shipment is succeeded. And that transaction have maybe multiple steps. But maybe after the first step, another request comes and you start writing in your log. So essentially that ledger that you maintain, you're adding one action at a time, but we may start adding concurrent action. So now it goes back to our serializable theory, is that this ledger that we're maintaining, one way of looking at it is that any conflicting operation needs to follow an ordering, and that ordering needs to be a serial one. So that's one way of thinking about maintaining a log, relating it back to concurrency. But now let's, for the sake of the problem, saying transactions has only one operation to simplify it. So now we are a bank. We have a ledger. Every time we get a transaction, we write it in our ledger, and another transaction, and so forth. This becomes a long journal of writing various transactions. Okay, that's good. So now the question is, what if this bank that is holding the ledger lose the ledger? Then what happens? Everything is gone. We don't, because that was the only copy that we had. We can no longer recover it if for whatever reason that is lost. Also, what if some malicious entity that holding that ledger goes back and changes things? This has actually happened in the past as well too. You had double entry in the ledger that was physically maintained, and so one thing that needed to be done to make sure these ledgers that are literally was maintained by people is there was no double entry in it. And later you can go back and change what the history was. So now we have two problems. Is that what if you're only maintaining one copy of this ledger, what happens if that copy gets corrupted or gets lost unintentionally? Or what if that ledgers was, because you have now full trust, nobody else is maintaining the data except that bank that has the ledger. So what if that bank become malicious and tries to change that? There's nothing really we can do. That's the ground truth. Whatever that bank says, everybody has to trust. There's nothing we can do. So now in the whole concept of the blockchain, the question is, well, instead of trusting with the bank, having a single ledger, what if every one of you, for example, that are on the call, you pick up your own notebook. And every time, for example, I announce that Alice paid Bob $5, you all go write on your ledger, on your notebook, that Alice paid $5 to Bob. And then once you do that, then I could, for example, ask for a vote and says how many people agree to that and how many people were able to write that. And if the majority say yes and vote yes to this transaction, then we could announce that, well, we all accepted it in a decentralized, in a democratic way, that Alice paid Bob $5. And also there's multiple copy of it because the majority of you who voted it yes have your own copy of the ledger. So it's decentralized in that sense, and it's also democratic because we didn't trust a single entity. Everybody participated, and everybody got a chance to vote on the validity of this transaction. So that's now that democratic and decentralized aspect of the blockchain. The other thing that comes into the blockchain is that you may say, well, why would I bother with picking up a ledger and maintaining that data? Why would I do that? You could say, well, it's an altruistic and you're doing it for the good of the society and you will be benefited from it. Those are all great arguments, but still one may say, what is the incentive to do this? Why would I spend the time and energy to maintain this ledger? What is it that I will gain from it? And so this is where the notion of the cryptocurrency and the Bitcoin came about, as saying, well, now imagine exact same problem setting. Everybody grab their ledger, everybody write down the transaction. And now imagine this. Every time I write on my ledger, I'm going to write one transaction that's say in every page of my notebook, just for simplicity. Every time I write one transaction on my ledger, on my page, once I finish writing that, imagine a random puzzle will just pop up. It will reveal itself once I write that. So everybody writes in their notebook, and then a random puzzle comes up, and everybody now go ahead and try to solve that puzzle. And whoever solved that puzzle first, that page of notebook turn into a bill, becomes a money, becomes a printed money. That page of notebook, just a Bitcoin gets created, whoever solves that. So now a Bitcoin gets created, a cryptocurrency gets created, and whoever solved that puzzle is given that cryptocurrency. So as we flip the pages of the notebook, you can think of it every time we write something to this ledger and flip the notebook, as we flip it, that flipping turns that page of notebook to a currency, to a cryptocurrency. And whoever solved that puzzle first, their name will be on that money that was generated. So that's how now cryptocurrency comes to be. Now the question is, well, if that puzzle is too easy, something very quickly can be figured out, then everybody was working on it together and everybody at the same time going to find an answer. Now, how are you going to choose who you're going to give that the prize to? So what the Bitcoin did says, okay, let's make this problem complicated, that not anybody can just easily find the answer. They actually need to invest resources. They need to spend time to be able to figure out what the answer is. And by the nature of making it difficult, it also the likelihood of two people getting the answer at the same time is also substantially reduced. So on average, the expected, if everybody's kind of working on this puzzle, on average, it is expected about 10 minutes it takes before somebody can find the answer. The actual, if you were just looking at an isolation, uh, trying to solve the puzzle on your own, I think the expected average that you find a successful puzzle is like 15 years, given some limited resources. So it takes a very long time because it's a difficult problem to solve, just a random problem to solve as a random puzzle. But on average, given so many different entities are working on it, we expect every 10 minutes a puzzle gets solved. So that means every 10 minutes also money gets printed. So this gives several benefits. So every 10 minutes, an incentive is created, and whoever solved that puzzle gets that reward. And also, given the difficulty of the puzzle, then it's the likelihood of many people find an answer at the same time is substantially has been reduced. And also, we can control the rate at which we print money. Because if you, because this is essentially now an economy. So if the central bank just print money if there's no tomorrow, it's going to cause inflation, and it's going to, from the economical standpoint, it's not going to be sustainable. That currency, whether if it's a crypto or non-crypto, it will lose its value. So also it is important to control the rate at which money gets printed. So that's another reason that you want to make sure that you have control. And also the other thing that it happens is that since every page is associated to a puzzle, then every time you add transaction and you solve a puzzle, this implies that if you were to just somehow let's say uh, all the notebooks were lost and somebody came out of nowhere say this is the right notebook, and for a few maybe, and we don't have any way of validating that, but at least we know to construct a notebook of having hundreds of pages, on every page a puzzle must have been solved. And so to solve a puzzle on every page and to construct such a fake notebook, it requires an enormous amount of computation. So probably not feasible. Most likely would not be feasible. So that's another aspect that brings resiliency. Faking a notebook, it's not easy. Faking an identity is easy. Anybody can start having a notebook, but going back and trying to catch up with this chain by just creating an alternative world based on your own notebook, it's a very expensive process because on every page you have to solve a puzzle. So creating a fake notebook becomes very expensive, almost impossible. But anybody can grab the notebook. And that becomes the interesting part, is that in order to vote, so when I kind of talked about the voting, in order to vote, everybody has a social security. In order to run an election, everybody has a social security. And using their social security, everyone gets one vote and participating in an election. So the number of votes is proportional to the number of valid identity of the citizen of that country. But in this model of voting using, for example, cryptocurrency or in blockchain, that anybody can just grab a notebook. Nobody's going to ask who you are. You just, as long as you have a notebook and as long as you can solve a puzzle, you can participate. And in this model, the barrier to entry is not having a social security. The barrier to entry is the demand that you need to solve a puzzle. So you cannot fabricate fake identity to get fake vote. You can create fake identity, but in order to get any reward or to get a vote, you need to solve a puzzle. So having thousands of fake identity, it's helpful for an election, a normal election, because you create fake ballots and they actually add up to the final result. But in the model of solving a puzzle, if you have fake identities and you can't solve the puzzle, those fake identity are useless. So that's another aspect of decentralization. There is no necessity of having a central authority to issue social security. Is that by the nature of this, the mining, and by nature of solving this puzzle, we create a barrier of participation in the consensus in terms of getting that reward, getting that success. So that was, I guess, a long analogy, but let me know so if you have any question on that.
But there is like someone still controlling the amount of currency, right? Like, so it's not really a democratic system if, like, there's this case, right?
So there is a lot of problem with this system, with this paradigm, but can you explain to make sure that I kind of know exactly which case are you referring to?
Like, we call it like a non-centralized way of currency, but in some cases it is still very much so like controlled by other people, right?
But can you give me an example how? Because I want to see what use case are you, or what scenario you're referring to.
Like I would say, like you said, the puzzles. They control how hard it is, like how fast people can solve it, right? And that's how much currency there is available, like to go around. I would say, right?
So so that rate is the assumption is you kind of trying to keep it around 10 minutes. And so the creation of a new block, a new piece of currency, which is, so that's like every 10 minutes. And that's something that was started from the beginning. So the system can just adjust itself to make sure that that 10 minutes is met. So that I think I don't think it's really a centralized control, is that the system needs to have a protocol to sort of make a progress. And people who participate in this, they think that they agree that this is a good way of doing it. So there was an agreement on that. So I don't think that's necessarily controlling it. However, there is absolutely a non-democratic process in here. And the way this non-democratic process here is that, as I mentioned, if you're just kind of a single individual and you want to kind of use your laptop to mine and solve the puzzle, most likely you will not be successful. And so what end up happening is that there are these companies that create what they call farms of huge warehouses of computers, and this warehouse is just for solving bitcoins, for solving these puzzles. So enormous amount of energy, and we're talking about large scale. And then they will kind of maybe sell shares. So for example, you can go to one of these farms and buy some quota, and so just buy some share of their resources, and whatever rewards they get, you could get some. You will get some. Whatever rewards they get, you also get a piece of that. So overall, you put an investment into that farm, and then there is a potential interest and reward that you're getting on your investment. And when you're actually looking at the distribution of the power, distribution of the computation to, for example, run Bitcoin, shockingly, there's 4 or 5 entities that have the majority of the power. So coming back to your questions, it ends up to be that 4 or 5 entities actually has the final say. It's really going to be a consensus if you kind of be yeah. So I think you could argue that that idea of the decentralization, it's now among 4 or 5 people who have the control of the whole power. So it's not a democratic or decentralized if 4 or 5 people having control. If you look at the original banking system, each country has a central bank, and each central bank will participate in the global financial system, and there is exchanges among the central bank of every country, and there's probably at least 200 different central bank in the global market, if not more, that probably have uh, a say or maintaining that ledger, that global ledger. So that seems to be a lot more democratic than having 4 or 5 entities controlling the Bitcoin in theory, well, not in theory, actually in practice. So yes, so from that sense, yes, the ideal of it was very democratic. The ideal of it was very decentralized, but the reality of it or the implementation of it has become more and more centralized to the point that literally a handful of entities controlling the entire Bitcoin. Any other question? Again, that's a really important question to ask. So again, perhaps the takeaway, I think this image, this analogy is all the blockchain is. Everybody grab their own notebook, everybody maintain a database or the ledger, and if everybody agree on what is written to the ledger, then there is a democratic vote. And also, since everybody has their own ledger, it's decentralized and it's replicated. And so that's the basis of doing consensus. That's the basis of, I would say, maintaining a distributed ledger. Now, one form of doing consensus, as opposed to actually doing a voting, so we could say we can do this example of voting by assuming everybody has an identity. And if everyone has and so we don't have to try to decentralize the generation of the identity, we can work with our social security. And so with our social security, we get a vote and then we do a voting protocol. But if you want to also eliminate the need of voting protocol, in the sense you don't want to reveal your identity, then proof of work, which is the basis of solving that puzzle, which is proof of work. You prove the work you did by showing the answer to the puzzle. You don't need to have an identity or a known identity or reveal your identity, and you can still participate in a problem in this consensus. And every time you solve a puzzle, you get a reward. So trying to building a democratic and decentralized system based on incentive, as opposed to building a democratic and decentralized system based on morality and ethics. So that's also an important social aspect to this. So it's not. So I think the problem goes broader than just computer science, and I mean there's a lot of economical, philosophical aspect to this problem of decentralization and democratization. Again, I mean, recently we had an election in the United States, for example. I mean, the importance of the election, importance of that, the process of democracy, it's one of the foundation of modern society. So we are talking about really important and profound concept here that goes, I think, just beyond computer science. So again, those are, I think, those are important. Why you want to don't want to reveal your identity and participate? Well, there is a case, for example, maybe for the notion of privacy. Of course, at the end of the day, often transaction results in exchange of physical good. To get a physical good, you need an identity. So whether you really need to hide your identity in terms of transaction, I don't know. Maybe it's not I'll leave that for you to think about. It could be a questionable could be questionable. And it also, by not revealing your identity, it creates hole into the regulations, and could be a platform to do money laundering, could be a platform to doing malicious activity, basically. So that could be another side effect of such system. And I think, again, so that's something important to consider. Any questions? Again, I really want to kind of explore these different concepts, because oftentimes there's a lot of hype and then there's a lot of misunderstanding about the whole problem or the whole concept of blockchain and its promises and what it can or what it cannot do. So I think it's important to simplify it and just look at it just at its core and what it really provides.
I have a question. So like, who are the miners? Like what do they, so they're the one creating blocks. Like how do they like gain any physical goods in general? And like, why are they able to create blocks?
Yeah, so that's a great question. So the way the whole blockchain in sort of the pure Bitcoin style works is that identity is, you can just on your computer create a public and a private key. And so you only have access to your private key. That means if you have encrypted something that can be verified using your public key, but you're the one who can decrypt it, or vice versa. You hold the private key, you hold the key, and only your public key is known. So that becomes your identity. You just say, this is my identity, and you can say this is my bank account, and your bank account is associated to a public key. A public key doesn't have any name attached to it, and anybody can generate a public key. And in fact, you can generate hundreds of public keys. So you could have, instead of having a single bank account, you could have hundreds or thousands of public private key. And every time you want to transact, you use a different pair, you use a different public and private key. So that's how the anonymity comes into the picture. So you're known as a public key, and to use the money in that account associated to the public key, the only way to use it is if you have the private key. And the private key is something you keep it private, so nobody else can use that money unless they have access to your private key. So that's the basic high-level model. And now, in terms of how do you participate, you just download the Bitcoin software and we can just participate. You say, okay, you generate a public-private key, you download the software, and you join the Bitcoin chain, and you download the existing part of the chain. So whatever blocks, whatever has been sort of added to the ledger, you download the current ledger, and then you start grabbing a bunch of transaction that needs to be executed. Everybody grab transaction, you grab a bunch of transaction, and then you write to your ledger. And as soon as you write it to your ledger, or you write it to a block, and once that block is filled with transaction, then the puzzle comes. Then you solve that puzzle. And when you solve the puzzle, you tell everybody, here is a block of transaction that I just added to the ledger. Here is the puzzle that is associated to it. And here is the puzzle that I solved. And everybody looks at it and they say, okay, yeah, you were right. You create a new block, consists of set of transaction, and you solved the puzzle correctly, and they all agree, and they add it to their ledger. And once everybody adds it to the ledger, then that becomes accepted. And as part of that block that gets generated, new block, also every new block is associated to a bunch of Bitcoins. So right now, and that number changes. Right now it's about 12 Bitcoins. 12 Bitcoins times the price of Bitcoin, that, I don't know, is 30,000, 40,000, I don't know what the number is, goes up and down like crazy. It's hundreds of thousands of dollars. So that block that you created worth a lot of money. And that money is going to go to your public key, to the bank account or to the virtual bank account that is associated to the public key. So on the ledger itself, now it says this new block that was created, 12 Bitcoin was just minted out of thin air because of that creation of that block. That 12 Bitcoin is going to be assigned to the public key of the person who solved the puzzle. Now on the ledger itself, 12 Bitcoin was created, and that 12 Bitcoin is associated to whatever public key of the person who solved that puzzle. And that's how, so the first block in the Bitcoin is 12 Bitcoin. The second block, another 12. The number was different, but just for the sake of the example. The first block is, let's say, 12. The second block is also 12. The third block is also 12. So if the ledger now has 10 blocks, there are 120 Bitcoins in the economy. There's only 120 Bitcoins. The only way to generate blocks, the only way to generate coin, in order to generate this cryptocurrency is to add a block. Every time a block gets created, money gets minted. That's why they call the problem of solving a puzzle of mining, because you're mining for gold. And so, and then it gets minted. Money gets printed, gets minted. So that's how the money gets generated. Whoever solved that puzzle, whoever solves it, they also give their public key. So that money goes to the public key. In order to use that, you need to have the private key to use that money. And the only person who can use it is the person who keeps the corresponding private key of that public key that money was assigned to it. If you lose your private key, that money is gone. And so each person has a digital wallet. For every public key, they kind of maintain their private key in their digital wallet. And as long as you keep your digital wallet safe and you still have access to your digital wallet, you can unlock those money that are associated to the public key for which you have your private key. And it happens some people, their computer dies, their digital wallet is gone, millions of dollars on Bitcoin just gets vanished. There's no way to recover it. For example, if somebody dies and it doesn't pass on the digital wallet to their, for example, to their spouses or to their children or to their parents, that money is gone forever. There's no way to recover it. So that's the sort of the financial management aspect of it. Does that answer your question?
Yes. And like, I don't know if this is legit, but like, if the miner creates the block, why can't they just solve it themselves?
So that's a good question. So the creation of the block, block is just 1 megabyte of data. And as a miner, you could just take an empty block. You don't even have to put anything into your block. So there's a bunch of transactions that needs to be executed or outstanding to be executed. As a miner, you can just grab any batch you want, doesn't matter which one. You can choose whichever you want to take. You can actually choose not to take any transaction. You can just create an empty block. This empty block needs to point to the previous block, to the last block in the chain. That means it needs to have a hash of the last block in the chain. Okay? So even if your block is empty, you still need to write in the block the hash of the previous block. So there is some content that is going to be on that block. And based on that content, you generate a puzzle, a deterministic puzzle is generated, and then you need to solve that puzzle. So you still need to solve the puzzle. And it may just be, there's going to be your public key saying that this block, I generated it, so the money should go to me. So there's few pieces of information in that block. Even if you don't take any transaction, take an empty block, you need the hash of the previous block. You probably need your own public key so that you get the reward. And then you solve that puzzle based on that. I mean, the puzzle is just, it's just the hash value of whatever this content of this block is. So as long as there's some bits in it, it's a non-zero value, and then you solve that puzzle. And the puzzle gets generated, and you solve that puzzle. And the fact that you need to always point to the previous block, that's essential, because if that wasn't the case, if you wasn't pointing to the previous block and it was just the empty block with your public key, you could just try to solve that ahead of time. But the fact that it needs to point to the previous block, you can only start solving the puzzle when you know what the previous block in the chain is. So that puts the starting point. Everybody can start solving the puzzle at the same time. So you cannot have the advantage of ahead of time pre-solved mini puzzle and you just kind of give the puzzle out. You can't do that. So that's essential. So that's the only essential thing. Now the question is, why do I bother of putting anything in my block? Why not just always solve an empty block and just get the reward? The reason is that every time you put a transaction in your block, you collect a set of transactions. And the people who put out those transactions, there's a fee to it. They say, whoever pick our transaction, we give them some fraction of Bitcoin. So when you collect a set of transactions and put it in your block, your reward is two-part. Your reward is for solving the puzzle, and all the transaction fee the sum of all the transaction fee that you have grabbed. So that's why if you want to maximize your gain, so you want to also fill that block with transactions, so you can so you get a lot of transaction fee as well too. So not just get a fee for the generation of the block, but you get the transaction fee. So that's an incentive to create non-empty block, having transaction fee. Otherwise, if you didn't care about transaction fee and you just wanted to create a block, Bitcoin could potentially be functional, probably not useful, but functional, just creating empty blocks, and every empty block is creation of Bitcoin, and that's fine.
Cool, thank you.
But now the question is, so then why not just create empty blocks? Why do we bother with that? Why wouldn't Bitcoin degenerate to a chain of empty block? And the reason is so now we need to talk about money. So in terms of currency, it used to be in the old days that money was a precious commodity. For example, you had gold coin or a silver coin. So the money had an intrinsic value to it because it was gold, and gold is a precious metal. It's used for jewelry and so forth, but it has enormous amounts of different values in so many different industries and manufacturing processes. So it's a very precious metal. It has very important properties. So the actual physical money itself had value because you minted it at gold. But later on, when you start printing money and you weren't handing out gold coin, so what the central bank would do, it says, okay, in our reserve, we're going to have all this gold, and based amount of how much gold we have, we can decide to print money. So the American dollar, or pretty much any other currency, was backed by gold, or backed by some form of something that had a value. But then even the American dollar, for I think in the 60s or 70s, I think it's in the 70s, they stopped being backed by gold. So there's nothing actually backs up American dollar right now. The only thing backs up American dollar, or in general the economy, is the perception. It only has a perception. There is a perception that American dollar has value. There is nothing else beside having a perception. And that's the volatility of the financial market. Is about perception. There's nothing that is really backed that up. And in fact, for currency, it's even worse, because there's not even the amount of money that, if you were to sort of sum up all the money that in everybody's bank account, There's not even a print money corresponding to that, because you loan it to this. It's just digital transfer of digits from one account to another account. You're loaning it. It's even the amount of the total amount of money in the currency in terms of American dollar not only is backed up by dollar, it's not even backed up by printed money. So it's a perception. There's a perception that the United States as a country or any other country, their money is valuable. So, and the only value of the Bitcoin is because there's a perception that this is a viable solution as an alternative to American dollar. American dollar has no backing. Bitcoin has no backing but the perception. So if we were to just create empty blocks, meaning nobody's using the blockchain, or the perception of the usefulness of this technology, if there's no actual transaction that goes into it, it's not used for anything. It's just an arbitrary way of creating nothingness, empty blocks, then there would have no perception and it would have no value. So the value would go down. So because there's no utility for it. But now since there's a utility for it and there's a perception that this is a valuable technology and it could potentially replace existing banking system or an existing financial system, then there is a perception. There's a perception of value, and that's where it gets its value, and that's why it fluctuates a lot. One day $7, $10. I think it reached $40,000, and they're betting on it to hit $100,000 per Bitcoin, and so forth. It's a gambling. I would say it's no different than gambling. So, and that's where that perception comes.
So I have more, I guess, ethical question in general. Like, so the limit of Bitcoin is, or the number of Bitcoin that we can have is static. So can't technically a certain set of people buy a large portion of Bitcoin and have a monopoly in a sense over the currency?
Yeah, so that's a good question. So Bitcoin, the reward of the Bitcoin is divided by half as more blocks periodically, as more blocks is generated, it divides it in half. So right now, the reward of creating a block is 12 coins, and in near future it could be 6 coins and then 3 coins, and that gets kind of reduced. So that's one thing. And as the number of rewarded Bitcoin gets reduced, the potentially transaction fee that the user needs to provide goes higher to compensate for this computation. One use case of the Bitcoin is that it allows anybody to transfer money to anyone without being inside the banking system. Right now, if I, for example, want to transfer to you, I have my bank, and somehow my bank needs to talk to your bank and do a wire transfer. It has lots of loops and hoops you have to go through to transfer some money to a friend or a third person. Bitcoin really eliminates a lot of that friction. And so it eliminates a lot of that friction, and it also reduces the transaction fee. So for example, to do a money transfer, you may have to pay $50 wire fee, or some union, there are other entities that transfer, they may get 5% of the money of the transfer. So the transaction fee is really high. So one other, in addition to kind of really open that up to anybody can just pay anybody any money without having an identity, it also has reduced the transaction fee. So exchanging money is becoming a lot more economical. Of course, as the reward for creating a new block goes down, the transaction fee is going to go up. And this benefits of having low transaction fee on the Bitcoin versus typical financial banking system, that benefit will probably vanish sooner or later. So the only thing will remain is that reward system. And I'm not sure if I answered your question, to be honest. I forgot because I was gonna give you some background. What was the question again?
Just more or less more of an ethical kind of idea, because people can technically buy up all the Bitcoin and just
Yes.
Never
So,
used
okay.
it.
So,
Yeah.
so I was just kind of giving you a background in terms of how, again, on the Bitcoin side. So now, what is it that if I go ahead and buy all the Bitcoins? Well, you can't really buy Bitcoins. Uh, so, so the question is, first of all, so you could say exchange this amount of Bitcoin from this account to that account. Okay. So, and presumably when somebody give you that exchange, maybe under the outside the blockchain, maybe under the table you give them money, under the table you give them some goods. So something needs to happen. So if you start kind of going to everybody and say, okay, I'll give you something and then you give me your transfer the Bitcoin to me, sure, that's good. You get all the Bitcoin, and let's just assume you have all the Bitcoins. And then what? You're having all the Bitcoins, and and since you're not transacting with anybody, because if you do transact with anybody, that means since you have all the Bitcoin, then in order to have a transaction on a Bitcoin, you need to give money to somebody. So no transaction is no longer going to happen, and so nobody's really going to be interested in Bitcoin because nobody can do anything with it. Nobody even has a Bitcoin, and instantly the price of Bitcoin will be zero.
I see. Thank you.
Yeah, and then as the comments, yes, absolutely. So if you lose your digital wallet, you cannot recover it. Yes, that money is lost forever, unless you can solve the problem of, I guess, P versus NP problem, or you have enormous amount of compute power beyond today's capability. Yeah, so that's to that point on the chat. Any other questions? Okay, so I guess I'm glad that we covered this slide. So we can go to the next slide. This is kind of just an overview of showing the increase in the data and why there is a need, for example, to partition the data, because there's just the size of the data is just increasing at an exponential rate. Of course, these are not transactional data. These are more analytical type of data. So this is more aligned with the fact that if you want to do a transaction analytic at the same time. And a lot of them are just sensor data as well too, something that maybe is not even, has nothing to do with the transaction data or the data from like the satellites or the different scientific experiments. Of course, with the sensor data, which again, there's enormous amount of sensor data that is coming in, at this point is we're not really making actions upon it. Maybe it's starting, but it's not really there. For example, you can imagine a self-driving car is getting all this sensor, and if that sensor data becomes fully actionable in a sense that if I get this data, then I make a right turn or make a left turn, and if you make the wrong turn, then there could be fatality and crashes. Then you can think about this enormous sensor data that comes in. If they become actionable, then in a sense become transactional, meaning that you need to make sure that the decisions that are made upon these data are, they have some correctness guaranteed around it, that you can talk about it, some form of a semantics around it. Then they could become a transactional data at that stage. Nevertheless, there is an increase. So there is a need, or there is a clear need that you cannot just maintain all your data in a single machine because, well, there's a lot of data. So that kind of sort of justifies or motivates the need of looking at databases that can partition across many machines, not just within a country, within a region, but potentially globally. So again, something that we've already talked about, I guess I could have maybe switched to these slides when I was talking about the basics of the ledger, is that this ledger is nothing but just a set of blocks, and each blocks points to its previous block. Each block has a puzzle. Each block holds a set of transaction, and that's just the basics of the blockchain. And every time you create a new block, a new puzzle gets created. That's going to be like a puzzle 4. And as part of that block, since you also keep a hash of the previous block, which is the hash of the third block, then even if you didn't put any transaction into this block, making the transaction part of this block is empty, since this block still needs to maintain the hash of the previous block, then you couldn't have foresees what the hash of the previous block is going to be. So you could have everybody can just start solving the puzzle 4 once puzzle 3 is completed. So it makes sure there's no advantage in the starting point. So that's important. And also, since in order to, if 4 blocks have been already created and accepted it, I could potentially create a new chain and pretend that this was the real chain. But for me to do so, I need to be able to solve at least 4 puzzles while this chain is continuing to grow. And what happens in the blockchain, the longest chain wins. So if I'm creating an alternative chain, not only I have to keep up with the existing chains, kind of go back and reconstruct this, but I also have to make sure that is longer. So that means I have to solve puzzle at substantially higher rate. And given it's already very computationally expensive, it's not something that is feasible to do, and that gives the protection to the chain. But it is possible that, again, if 2 different people at the same time solve the puzzle, then a fork could happen. So one person solve the puzzle for the second block, there's a B2 and the B2 prime. And so that's possibility, fork does happen, but the longest chain wins. So whoever get the third block and the fourth block attached to them, this becomes the winning chain, and the other chain is just simply get discarded. And in fact, for a transaction 101, let's say, you only say that this transaction is finally settled if 5 more blocks get generated after it. So this transaction 101 is still not settled. In fact, transaction 1 is not settled because there are not 6 blocks yet. So if your transaction goes into the first block, you wait up to 6 blocks, it gets created. And once 6 blocks get created, that means your chain is long enough, is now 6 blocks long at least, then you can say that transaction was settled. So it may take an hour, because if each block takes about 10 minutes, so it takes at least an hour for a transaction to get settled. So that's another kind of challenge with this model. But then the reason you wait 6 blocks, because the possibility of having a chain because it's possible so this 2 blocks gets created, the third block gets created here, and somebody else tried to extend this. And now, if you have a fork, essentially your computation could potentially be split, or maybe it's not exactly perfectly split. In practice, won't be perfectly split. So at some point, one side would have a bit more computation and gets ahead of the other one, and eventually, 6 long. If you wait 6 blocks, the probability of still having a fork is virtually 0. So that's why if you wait for 6 blocks to be added to the chain, then you can assume that your transaction settled. Again, it's just an empirical observation. which is based on the probability of chain happening and the complexity of the problem. So it's a very safe bet. If you wait for 6 blocks, then that transaction will be completely settled. It hasn't been in the case to suggest otherwise in practice. So I think it's now 3 o'clock. So any questions?
Professor,
Yes.
before you said that the longest chain wins.
Yes.
So what determines whether like part of the chain gets attached to a previous part of the chain?
So consider this case is that assume that B3 and B4 wasn't there. Is that we have B1, B2, and B2 prime. So, and then there is a fork. So from B1, we could either go to B2 prime or we could be at B2. So now there's a bunch of transactions. Let's say there are transactions from 201 to 300. So one miner grabs transaction 201 to 300, and that miner that now wants to do the next 100 transaction and create the block B3, it needs to spin off from some chain because it needs to put the hash of the previous block into its block before it can start solving the puzzle. So it needs to choose. It could use B2 or it could use B2 prime. Whichever it chooses, that's the one that is going to be built off against. And it could choose the wrong one. It might be that it hasn't seen the longest chain. And so even if it solves the puzzle, that all that work could go in vain. So it just depends. The miner, I'm solving a puzzle right now. I'm creating a new block. I need to decide to which chain I'm going to attach this to. And there may be multiple parallel chain that is happening. But we know that the longest chain will win, so the other chain will lose sooner or later. So if you're lucky enough and you pick the right chain to attach your block to, then you will win and you will get that reward. Otherwise, well, that's something that's lost. In fact, there is an attack called selfish mining, is that especially if one of these big entities that have lots of computational power, when they create a new block, they don't announce it. They keep it to themselves and they go start creating the second block. And doing this selfish mining, everybody's still maybe still working on a first block. They've already answered for that and they're already moving on to the next block. So they can actually use that as a way to get ahead. And then once they have few blocks, then they say, here you go, we found all these blocks, and basically invalidate everybody else's work that was done maybe in the last hour or so, for example. So those attacks are very well possible.
Thank you, Professor.
Thank you. Any other questions? I mean, I'm not going to go any farther today, so that's kind of our stopping point. All right, so if no further questions, have a wonderful day, everybody. Thank you.